So what we want to look at today is this concept of what's known as rectilinear motion, also sometimes called kinematics. All right, the idea there. But the whole idea of this is similar to the example that we were looking at with the diver, where there are multiple dimensions, obviously, in real life, but we're only focusing on one dimension of motion. Okay? We can consider it as moving across a number line or moving up and down. Okay? But really, it doesn't matter which way the movement is as long as we're only looking at one dimension at a time and we're looking at it as a function of time. Okay? So here we're looking at an independent variable of time, and then we're looking at three different things related to the motion. Okay? So the first of these things is the displacement. Okay? Now the displacement is a vector distance from the starting point. Now when we say vector distance, that means it could be positive or negative, because the positive and negative indicates which direction we went from the starting point. Okay, so if I'm standing here and this is my starting point, if I'm moving over this way, 2 spaces to your left, I've moved to -2 at my displacement. Okay? If I move over to your right, 3 spaces, now I'm at +3. So if I said -2 or +3, you would have known which way I was from my starting point. Okay? So it's a vector distance. Those of you who had SL, we used S of t instead of x of t. You'll see both of them used. But then, if you think about this, if I'm looking for how quickly our velocity or our position is changing, I'm looking for velocity. Okay? I'm looking for velocity. So since it is a rate of change, I'm going to find a derivative. Okay? The derivative of our displacement with respect to time is the velocity. We could even write that as x prime of t. In fact, you might see it more often written that way than just dx dt. Okay? We'll use both. But now, a key thing to note here is that this is instantaneous. All right? In our example with the diver, like we had said, it took us 2 seconds to hit the water. And we went down 32 feet because we started 32 feet above the water. Well, that 32 over 2, negative 16 feet per second, that would have given us an average velocity. Okay? That's not what we're talking about here. We're talking about at any instant, how fast or what is the velocity of this object. Okay? So, velocity is the first derivative of the displacement. Now, acceleration. Acceleration is the rate of change of the rate of change, right? It's how quickly our rate of change is changing. So if you're just driving along in your car and you have it on cruise control, your acceleration is 0 because you're staying the same speed the whole time, the same velocity the whole time. However, when you hit the brakes or when you hit the gas, now your velocity is changing. You have acceleration. Okay? So, now acceleration is the instantaneous, again, rate of change of the velocity. I want you to see where this comes from, though. We can see the acceleration as the derivative of velocity. Okay, so we could write it as v prime of t. Or, if you think about it, it is the derivative with respect to t of the derivative of x with respect to t. Okay? That's what we're doing here. We're taking the derivative of x. And that's why we have this notation. Notice there are two d's there, so that's why it's d squared x dx squared. Okay, and actually there's a typo on here. This x right here should be a t. Okay, this right here should be a t. Okay, so you can fix that. But that's where this comes from. Now, another way that we can write it, since we took the derivative of the derivative, this is what is known as the second derivative of x. Okay? That's the second derivative of x. Now, we haven't done second derivatives, but it's really an easy concept. You take a derivative, and then you take the derivative of that. Okay? Pretty simple. But that's what gives us our acceleration. And then speed. Speed is the absolute value of the velocity. So we're taking away the direction component. Okay? There's some Cars fans in here. Right, so we have the magnitude of the velocity is our speed. That's a simple thing, but please be careful to what you're being asked to find. Okay? Read the question carefully. If they ask for a speed, you shouldn't have any negatives. Okay? If they ask for a velocity, you just do the derivative and give what it gives you. Okay? Yes?
Why for a of t, why isn't it d squared as well on the bottom?
It's like the dt is with respect to t is kind of like a unit there. So it's not really multiplication. dt is like a thing all by itself.
It's one, okay.
Yeah. Yes.
So for the last one, if we were to do acceleration, would we have plugged in 2 into the second equation? Or, I guess the third equation we would have had? The third or the second derivative?
Oh, with the diver?
Yeah.
The diver we had the velocity was negative 32t plus 16. The derivative of that would have been negative 32.
Oh, okay.
The acceleration was negative 32. Now think about this. What's the acceleration when we're falling? Gravity, right? Which is negative 9.8 meters per second squared, or negative 32 feet per second squared. Okay? That's why I came out to negative 32. All right, so, and that's going to be true no matter how long you're falling, the acceleration of gravity stays the same. So, unless you're on the moon. That's totally different. So, but we'll stay on Earth. Okay, now, here's the part that is typically the most confusing part. And that is, are we speeding up or are we slowing down? And people tend to think that, oh, if the velocity is positive, that means we're speeding up.
That's annoying.
And it's not. Other people tend to think, hey, if the acceleration is positive, we must be speeding up. No, it's not necessarily, okay? This is a challenging thing. So the best thing I can think of to illustrate is, have you ever run on a slippery floor and tried to change directions? Okay? Or, I'll show you the video here. Alright, so that idea of, wanting to change directions on a slippery floor, and your momentum, you decide you want to change directions, but your momentum keeps you going the direction you were going. Until finally you're able to overcome the momentum, you have that moment when you stop going the other way, and finally you're able to start going the way you wanted to go. Okay? Is that making sense?
Yes.
Okay. So, in that event, if we were to draw this out, okay? Let's say that you are traveling this direction. Okay? And right here, you decide, I want to go the other way. Okay? I want to go the other way in your head. So now you start trying to go the other way. Yet your momentum is still carrying you this way. Okay? At that moment, your acceleration, well, here we have a negative velocity because we're moving to the left, right? In this case. We still have a negative velocity, but what would our acceleration be? It's positive. We are trying to go the other direction. Finally, we stop. That's velocity equal to 0. Now, at that moment, A is still positive. Okay? If A weren't positive or negative, if A were staying the same, or were 0, then when we stopped, we would just stop and not move anymore. But because our acceleration is still positive, guess what happens? Now we start to turn around, and now we have a positive velocity and a positive acceleration. Okay? So we see here, this is, that dog saw the other dog and decided to go the other way.
Actually, I think the acceleration is vector.
Is what?
Vector.
Acceleration is a vector quantity as well, yes.
Yes.
So the positive and negative means something. Okay?
Yes. So if it's going from the right to left is positive for the acceleration, it should be negative from the left to right.
Except you got to remember, acceleration is not something that we're necessarily able to see happening.
Yeah.
We can see the dog trying to go the other way. That attempt to go the other way is his acceleration in the other direction. That's what's making him slow down and then finally stop and then start to go the other way. Acceleration is what is changing our velocity from negative to positive.
So
Okay?
keeping adding the positive acceleration to the negative velocity.
Yeah, you're adding a positive acceleration to a negative velocity, and what does that do to your speed? You're slowing down right here, okay? So that dog, once he saw the other dog and decided he wanted to go the other way and started trying, he was slowing down, okay? Slowing down. Once he was able to stop and actually change directions and start moving in the direction he wanted to go, he started speeding up. Slowing down and speeding up has absolutely nothing to do with which direction you're actually going. It all has to do with the cooperation, you could say, of your mind and your body. Okay? Or the cooperation of what you want to do and what is actually happening. You can think of your acceleration as what you want to have happen, and your velocity as what is actually happening. Okay? So, let's look at this example real quickly here, and we'll see this in the table down below. Okay? So we have this object that's traveling in the x direction, and its displacement is given by x of t equals 3t cubed minus 30t squared plus 64t plus 57. And we're looking at this from time 0 to time 10, so 10-second window. Okay? Now, we can observe using our power rule the derivatives, okay? X prime of t is that velocity, remember, okay? So that is, in this case, a 9t squared. Bring the 3 out in front with the other 3. So 9t squared minus 60t plus 64 plus 0. Okay? Then we have acceleration. Okay? Acceleration at time t is the derivative of the velocity, or the second derivative of the displacement. 2 times 9 is 18, so it's 18t minus 60. Okay, so that's where they're getting those. All right. Now, look at the numbers they've got here. The object has stopped. This is something you got to get in your head as you're getting used to this. The object is stopped. That means the velocity is 0. Okay? How do we figure out when it stops? Set the velocity equal to 0. Okay? So up here we would set this equal to 0 and we would solve it. Okay? So in this case here, you know, t equals when it stops. If it equals 0. Okay? Now, if you were to solve that equation, you all can solve a quadratic. You'd get t equals 1.33 seconds and 5.33 seconds. Okay? Now, acceleration equals 0. Acceleration equaling 0 is when we're either moving at a constant rate of speed or a constant velocity, okay? Or, specifically here, it's the moment when we decide we want to change direction. So like in the video, it's when the dog saw the other dog. That moment was when the acceleration was 0, because it changed from accelerating the one direction to trying to go the other direction. Okay? So you could think of it as in terms of when we decide to change directions. All right? And again, I'm using an analogy here because I think it's helpful to really understand this speeding up and slowing down thing. Okay? Now, you see this table at the bottom. This is sign analysis. This kind of a thing is very, very important to be able to do. Sign analysis. All right? To make this table, we're comparing our time, our velocity, and our acceleration. The times you're going to fill in based on all the stuff we just recognized. Okay? Notice we have the starting time and the stopping time. Start and stop. Okay? That's from our domain, 0 to 10. Okay? Also, when we're doing a sign analysis, we're going to use when the object stops moving from left to right. Okay? So, here v equals 0. That's when we stopped. We stopped going to the right. Okay? stop going right. I'll just put R. Okay? At 5.33, you'll notice this negative velocity between 1.33 and 5.33. That means we were moving to the left. Okay? Or downward, but in this case it said the x-axis, so it is to the left. Alright? So at this 0, that means we stopped moving left, or we stopped going left. And then, of course, right here, that's when we decided to change directions. That's when our acceleration equaled 0. Okay? So you're going to use the zeros of your first and second derivatives and the ends of your domain to form your sign analysis. Okay? So now it's just a matter of filling in the table. Okay? We're going to fill in the table here. Obviously, the ones that are zeros we already know because that's how we got those numbers. Okay? But all you need to do here at the start with 0, you plug in 0 to your velocity and your acceleration. The velocity is positive, 64. The acceleration is negative 60. All we really care about is the sign itself. So velocity is positive and acceleration is negative. Okay? So we're moving to the right, but the acceleration is actually slowing us down there. Okay? Finally, we stop for a moment and we change directions. We're going to the right, now we're going to start going to the left. Okay? Now, in that range between 1.33 and 5.33, if we plug in the 3.33, the velocity is negative. And then at the end, if we plug in 10 to the velocity, we get a positive number. Okay? So what this tells us is, change colors again here. Here we're moving to the right. Then we stop, then we're moving to the left, then we stop, now we're moving to the right again over here. Okay? Now understand here that these are intervals. Okay? It's not just at that one time. So, when it asks us when is the object moving to the right, it's the time from 0 up to 1.33. Okay? Now, notice I used an open parenthesis here because at 1.33 I'm not moving anywhere anymore. Okay? So make sure you're careful with the notation. Also here, I'm moving to the right from 5.33 up to 10. Okay, we can put a little union in there. Those are the two intervals where this object is moving to the right. When are we moving to the left?
1.33 to 3.3.
From 1.33 to,
Oh wait, no, yeah.
yeah, up to 5.33. Okay? And I'm going to use parentheses on both of those. Now, here's a part that's a little bit challenging, okay? When are we speeding up?
During the
Okay, so from
No, from 5 points.
okay, from 5.33 up to 10. Okay, this is an agreement. Okay, so not exactly at 5.33, but after 5.33. Up to 10, we are speeding up. Okay? Notice though, we're also speeding up anywhere that we're in agreement here. Notice between 1.33 and 3.33, the acceleration is negative and the direction is negative. That's going to make us speed up. Okay? 1.33 to 3.33. Okay? So again, you got to see the intervals. Even though we have boxes in this little table, you got to see the intervals. It's going to slow down. It's going to slow down to the left of 1.33. Okay? And it's also slowing down between 3.33 and 5.33. That's when it is slowing down. Okay? Because in those cases, we're in disagreement. From 0 to 1.33 and between 3.33 and 5.33. Okay? All right, we'll stop there. Have a great weekend. We'll see you on Monday.
Thank you.